Hi friends, welcome to my YouTube channel. As I told you in the previous video, as I promised, I am sharing the video regarding the strain energy due to bending, torsion and shear. So first, see the strain energy due to bending. See, coming to this, we are considering a beam that is rectangular, subjected to the series of loadings and the moment caused because of this loading, that is supported at two ends. So from bending equation, we know that m by I is equals to stress by y, where this is the stress. We need stress. So that is simply m by I into y. Okay, from the previous derivation, that is derivation of the strain energy due to the loads. Loads due to the gradual load, sudden load and impact load. We have discussed the work done is equals to half into the load into displacement. See, this is what I am talking about. The work done is equals to this, the load and deflection. I have also shown the derivation of this formula, how we will get the work done in our previous video regarding the strain energy due to different applied loads. If you haven't checked that video, please kindly go to the channel and view that video for clear and detailed explanation regarding the applied loads and basic understanding about the strain energy. I have also mentioned the strain energy definition and all the terms regarding that in that video. Kindly check it out. Now coming back to this work done, this is the formula. So we need strain energy, that is du, the small elemental strain is, this is the formula. See, 1 by 2e is them, but we are just substituting the value of the stress from the bending equation over here. As I am saying, this is a small element, the area would be dA and the length would be dx. Okay, so simply writing all the terms together, m square dx by 2ei I square y square dA. So this is the small strain developed. So whenever we are requiring, like we are deriving the total strain energy, this is the formula, that simply integrate it. Now we are integrating this equation of du. So I am taking this constant one outside. We know the integration of y square dA would be Ixx. Whereas Ixx is the product of, see, the centroid from center 1 here. This is the center 1 we are taking. We are considering a small element dx. It's between section 1 and 2. So this is Ixx from center 1. So from the above drawing and from the basic strength of materials, we'll get integration of y square dA is equals to Ixx. Simply substitute that over here. And this I and I would be cancelled. 1 by 2a is constant. This integration would remain over here also to this part. Simply keeping the integration. Next, we are taking the second derivation, that is strain energy due to torsion. Let me first explain you what is torsion. Torsion is nothing but a twisting movement. Twisting movement acting on the body. See here, the two equal and opposite direction forces are acting on this element. So this is torsion. As I told you before, work done is nothing but half into load into displacement. Here the load applied is twisting movement. Okay, this twist is the load, and whatever the deformation that is taking place is the angular deformation due to this twisting movement. This is theta. We know from this torsion equation, T by J is equals to G theta by L. From this we can evaluate the formula of theta. Simply substitute this value over here. This would be the equation. U is equals to T square L by 2JG. I will also explain you what all the terms are this. See, in this equation, as I told you, the strain energy developed due to the torsion or the twisting movement. I am telling you the terms. Next, coming to the third derivation, that is strain energy due to shear. We know the work done is equals to strain energy. Also, that is the work done we discussed, it is half into load into the displacement. Here, as it is equal, we will just simply evaluate this by using this formula. Here, whatever the P is there, that is the shear we are applying, right? The shear. And again, as this is a shearing moment, we will be getting the deformation as theta. Okay, so this is the equation. But first of all, we are just converting this theta into Q terms, just for simple evaluation of the formula. Okay. Again, from the second part of the torsion equation, we'll get this. G theta by L is equals to tau by R, where tau is nothing but the shear stress. See, we'll get the theta by this formula. We also know that tau by G is equals to Q by BD, right? Q by BD. So simply substitute this. Theta is equals to QL by BDR. We know that the shear modulus or modulus of rigidity is nothing but shear stress by shear strain. So when we need this theta is equals to Q by BDG. Simple. Q by BDG. Substituted in this, you will get tau is equals to G theta, right? Where theta is G, and again when we are multiplying it with G and G would be cancelled. Simply the shear stress would be Q by BD. Okay? But we are now requiring this theta over here. Simply just substitute this over here. You will get this equation. U is equals to Q square 2BD G dx. We know BD is nothing but the area of that cross section, 2AG. Okay? Also, I am explaining the terms of this. Q is nothing but the shear force. Okay, shear force applied. Theta dx is shear displacement. G is modulus of rigidity, that is shear stress by shear strain. As I told you here, G is equals to tau by theta. That is it for this video, guys. Please like, share, comment to my channel. Please subscribe to my channel. That would greatly help me. I appreciate you watching this video. Thank you.